previous lecture. We transform rational functions to power series by substitution or differentiation. We also transform logarithmic functions using integration. Today, we will transform exponential, trigonometric, and hyperbolic functions to power series using the concept of Taylor series. So what is Taylor series? If f of x is an infinitely differentiable function, then the Taylor series of f of x about x equals x of o is given by f of x equals the summation of a sub n times x minus x sub 0 raised to n from n equals 0 to infinity, where a sub n is equal to the nth derivative at x of o over n factorial. So you have to recall higher order derivatives from calculus 1. So the Taylor series is also a power series where the coefficients are determined using evaluation of derivatives. Let us have an example. I will be using a quadratic function for my first example so that we can check our solution and we can verify the validity of the formula for Taylor series. So example 1, determine the Taylor series for the function f of x equals 3x squared minus 8x plus 2 about x equals 2. So to find the series, we have to evaluate the function and its derivatives at x of 0 equals 2. So first, evaluate the function at x of 0 equals 2. Given f of x equals 3x squared minus 8x plus 2, so f of 2 is equivalent to negative 2. We then determine the coefficient using the formula and derivative at x sub 0 over n factorial. So your a sub 0 is equivalent to negative 2 over 0 factorial or simply negative 2. Then we find the derivatives and evaluate the derivative at x sub 0 equals 2. So the first derivative is 6x minus 8. Evaluate at 2, you will end up with negative 4. That means your a sub 1 is equivalent to negative 4 over 1 factorial or negative 4. The second derivative is 6, and evaluating this at x sub 0 equals 2 will give you 6. So that means your a sub 2 is equivalent to 6 over 2 factorial or 3. The third derivative is 0, implying that the function value at 2 is also 0 and the coefficient a sub 3 is also 0. The pattern will continue. That means a sub 4, a sub 5, a sub 6, and so on will give us 0. After finding the coefficient a sub 0, a sub 1, a sub 2, and so on, we can now write the expression in series form. So using the Taylor series formula, f of x equals the summation of a sub n times x minus x sub 0 raised to n from n equals 0 to infinity. So at x sub 0 equals 2, we will end up with this expression. F of x equals the summation of a sub n times x minus 2 raised to n from n equals 0 to infinity. So in addition form, you will end up with a sub 0 plus a sub 1 times x minus 2 raised to 1 plus a sub 2 times x minus 2 raised to 2 plus a sub 3 times x minus 2 raised to 3 and so on. We then substitute the values that we get from a sub 0, a sub 1, a sub 2. So we end up with f of x equals negative 2 plus 4 times x minus 2 plus 3 times x minus 2 squared plus 0 and so on. So therefore, your Taylor series is given by f of x equals negative 2 plus 4 times x minus 2 plus 3 times x minus 2 squared. We note that the resulting Taylor series is a finite expression. It is actually a quadratic expression since our given function is also a quadratic function. So let us check our solution. So f of x equals negative 2 plus 4 times x minus 2 plus 3 times x minus 2 squared can be simplified. 2. F of x equals negative 2 plus 4 times x minus 2 plus 3 times x squared minus 4x plus 4. So that is the expansion of x minus 2 squared. So f of x equals negative 2 plus 4x minus 8 after distribution plus 3x squared minus 12x plus 12, another distribution. Then we combine similar terms and we will end up with f of x equals 3x squared minus 8x plus 2. So the Taylor series representation of the function was simplified and was transformed to the original function. Thus, the Taylor series works. Now, let us express an exponential function in series form. So, determine the Taylor series for f of x equals e raised to x about x sub 0 equals 0. So, for our solution, let us evaluate the function and the derivative at x sub 0 equals 0. So, f of x equals e to the x implies that f of 0 equals e raised to 0 or simply equal to 1. That means our a sub 0 is 1 over 0 factorial or 1. The first derivative is e raised to x. So the value at 0 is 1 and your a sub 1 is 1 over factorial, which is also equivalent to 1. The second derivative is e raised to x. So the value at 0 is 1 and a sub 2 is 1 over 2 factorial. The third derivative is e raised to x. So the function value at 0 is still 1 and your a sub 3 is 1 over 3 factorial. So by inspection, we can say that a sub n is 1 over n factorial. After finding the coefficients a sub 0, a sub 1, a sub 2, and so on, we can now write the expression in series form. So at x sub 0 equals 0, f of x is equivalent to the summation of a sub n times x minus 0 raised to n from n equals 0 to infinity, or simply summation of a sub n times x to the n from n equals 0 to infinity. In addition form, we will have a sub 0 plus a sub 1 x plus a sub 2 x squared plus a sub 3 x cubed. Let us substitute the values for a sub 0, a sub 1, a sub 2. So you will end up with f of x equals 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed and so on. Or in sigma notation, you will end up with f of x equals the summation of x to the n over n factorial from n equals 0 to infinity. So we end up with an infinite series that we can use for approximation. Now, what if the center is x sub 0 equals 1? That is, determine the Taylor series for f of x equals e raised to x about x sub 0 equals 1. So evaluate the function and the derivative at x sub 0 equals 1. We know that we will have the same derivative as the previous example, but the coefficient is now of the form e over n factorial. So f of x equals e to the x implies that f of 1 is equivalent to e to the 1, which is equivalent to e. So your a sub 0 is equivalent to e over 0 factorial or simply e. Taking the first derivative, the second derivative, the third derivative, and so on, we will end up with e raised to x. So f prime at 1 is still e, and your a sub 1 is e over 1 factorial or simply e. Your function value for the second derivative is still e, and your a sub 2 is e over 2 factorial. While the third derivative will give us a sub 3, which is equivalent to e over 3 factorial, or a sub n is equivalent to e over n factorial. So write the expression in series form. So this time, our center is x sub 0 equals 1. So we will end up with the expression summation of a sub n times x minus 1 raised to n from n equals 0 to infinity, wherein in addition form, it is equivalent to a sub 0 plus a sub 1 times x minus 1 raised to 1 plus a sub 2 times x minus 1 squared plus a sub 3 times x minus 1 cubed, and so on. Substitution of the values for the coefficients, we will end up with f of x equals e plus e times x minus 1 plus e over 2 factorial times x minus 1 squared, and so on. Or in sigma notation form, your f of x is equivalent to the summation of e over n factorial times x minus 1 raised to n from n equals 0 to infinity. Now, trigonometric functions can also be written in power series form using Taylor series. So let us determine the Taylor series for f of x equals cosine x about x sub 0 equals 0. So let us evaluate the function and the derivative at x sub 0 equals 0. So f of x equals cosine x implies that f of 0 equals cosine 0 or 1, meaning your a sub 0 is equal to 1. The derivative of cosine x is negative sine x, and the value at 0 is equal to 0. Therefore, your a sub 1 is 0. The second derivative is negative cosine x, implying that the function value of the second derivative of 0 is negative 1. So, a sub 2 is equivalent to negative 1 over 2 factorial. The third derivative is sine x. And you know that sine 0 is equal to 0. So, your a sub 3 is also 0. Let us take the fourth derivative. So, the fourth derivative is cosine x. And the value at 0 is 1. So, meaning your a sub 4 is equivalent to 1 over 4 factorial. So, by inspection, we end up with 0 for odd expressions. Now, let us write the expression in series form. So, using the Taylor series formula at x sub 0 equals 0, so we must evaluate f of x, which is equivalent to the summation of a sub n times x raised to n from n equals 0 to infinity. So, in addition form, a sub 0 plus a sub 1 times x plus a sub 2 x squared plus a sub 3 x cubed. We will end up with f of x equals 1 plus 0 plus negative 1 over 2 factorial x squared plus 0 plus 1 over 4 factorial times x to the fourth. Simplifying, we will end up with an even power expression. So meaning, the Taylor series for cosine x is equivalent to f of x equals 1 minus 1 over 2 factorial times x squared plus 1 over 4 factorial times x to the fourth minus 1 over 6 factorial times x to the 6 plus 1 over 8 factorial times x to the 8 and so on. Wherein we can say that we end up with an infinite series which is also an alternating series. So in sigma notation form, f of x is equal to the summation of negative 1 raised to n times x to the 2n over 2n factorial from n equals 0 to infinity. Note that 2n implies even expression and negative 1 raised to n implies that you end up with an alternating series expression, meaning the sign changes from positive to negative. So as a summary, here are the series representation of some transcendental functions that we will encounter in succeeding discussion. So Taylor series or Maclaurin series. So e to the x is equivalent to 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. Cosine x is an even function. So we end up with 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial and so on. While your sine function is an odd function, so we end up with x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. For hyperbolic cosine, we simply change the sign of your cosine expression. So it is all positive. While for hyperbolic sine, so you follow the expression for sine x, but the values must be positive. So we can use power series to evaluate definite integral that can be solved in calculus 2. So let us estimate the following integral using the first 5 terms of the series. For number 1, let us use an exponential expression. So evaluate the integral of e to the x squared dx from 0 to 1. And for number 2, let us use trigonometric function. Let us evaluate the integral of sine x over x dx from negative 1 to 2. So to solve, we are going to express the integrand in power series form and then proceed as in calculus 2. We note that e raised to x is equivalent to the summation of x to the m over m factorial from m equals 0 to infinity. So the exponent will serve as the base for the power term. So if we want to write e raised to x squared, then the base must be x squared. So e raised to x squared is the same as the summation of x squared raised to m over m factorial from m equals 0 to infinity. So to evaluate the integral of e to the x squared dx from 0 to 1, we are going to write this in power series form. That is the summation of x squared raised to m over m factorial from m equals 0 to infinity. From algebra, you know that x squared raised to m is the same as x raised to 2m. We then get the integral of x to the 2m, which is equivalent to x to the 2m plus 1 over 2m plus 1. So therefore, the integral of the expression is equivalent to the summation of x to the 2m plus 1 over m factorial times 2m plus 1 from m equals 0 to infinity. And we have to evaluate it from 0 to 1. But before evaluating, let us write first the sigma notation in addition form using the first 5 term of the series. That is x plus x cubed over 1 factorial times 3 plus x to the 5th over 2 factorial times 5 plus x to the 7th over 3 factorial times 7 plus x to the 9th over 4 factorial times 9. And then evaluate it from 0 to 1. So evaluating will give us 1.461772487, which is the integral of e to the x squared dx from 0 to 1. So for problem 2, express sine x in Taylor series, then simplify. So sine x is equal to the summation from m equals 0 to infinity of negative 1 to the m times x to the 2m plus 1 over 2m plus 1 factorial. Meaning, sine x over x is equivalent to the summation from m equals 0 to infinity of negative 1 to the m times x to the 2m plus 1 over 2m plus 1 factorial all over x. So let us divide the expression by x and we will end up with the summation from m equals 0 to infinity of negative 1 to the m times x to the 2m over 2m plus 1 factorial. Or in addition form, you will end up with 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial. So let us evaluate the integral of sine x over x dx from negative 1 to 1. First, write sine x in power series form. This time, we are going to use the addition form. That is, sine x is equivalent to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. And then, divided by x, ending up with 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6 over 7 factorial plus x to the 8 over 9 factorial. Then, find the integral of each term. And we will end up with x minus x cubed over 3 factorial times 3 plus x to the 5th over 5 factorial times 5 minus x to the 7th over 7 factorial times 7 plus x to the 9th over 9 factorial times 9. And then evaluate the expression from negative 1 to 2. Substitution of negative 1 and 2 will give us 1.605417542 minus the negative of 0.94608300726. So therefore, the integral of sine x over x dx from negative 1 to 2 is 2.551500615. So for this particular example, I write the series in addition form before finding the integral of the given function. So that's all for the discussion of Taylor series. Next time, we are going to discuss power series solution to differential equation. So this is Redentor Disles. Have a good day.